Hello everyone. My name is Yasus Timilsin and today I'll be presenting on the von Neumann architecture. So this architecture is incredibly important because it forms the basis of almost every computer system we use today, from laptops to phone and to servers. So my goal in this presentation is to explain where this model came from, what its components are, how it is actually executes instruction and why it still matters today. So here's what we'll be covering today. A little historical background about where the architecture came from. So the core components that every von Neumann machine includes, and the fetch execute cycle. In this, we'll learn how the fetch execute cycle works. So this is the heart of all computations. So and the memory organization too. So how memory is organized and why storing programs and data together was a revolutionary idea. And finally, the modern impacts. So the bottlenecks and modern improvements that grew out of this model. So this will give a full picture of how a CPU actually behaves underneath the code that we write. So talking about the historical context, so John von Neumann introduced this idea in 1945 while working on the EDVAC project. So before this, computers were basically fixed function machines. If you wanted to run a new program, you literally had to rewire the machine by hand. So von Neumann's insight was simple but powerful. Store program instructions in memory exactly the same way we store data. So this made computer flexible, programmable, and able to run many different tasks just by loading different codes. So the five core components. So this architecture is built around five main components. So first one is the control unit. So it directs operation and manages instruction flow. So the second one, it's arithmetical logic unit, also known as ALU. So ALU performs all math and logic. The third one, that's memory unit. So memory unit typically stores instructions and data together. And the fourth one is the input device. So it brings data into the system. And the final one is output devices. So that displays the results. So these five components are still present in modern day CPU. Even if today's chips are far more advanced, the structure is still the same. So let's see how the CPU works. Here we can break down the CPU into two major parts. So the first one is the control unit and the second one is the arithmetical logical unit. So the control unit, it fetches instructions, decodes them, and sends timing signals. So, however, the arithmetical logical unit, it performs operations like addition, subtraction, logical comparisons, bit shifting, and many more. So we can say it that the anytime you write an if statement, a loop, or a math expression, the ALU is the part of the CPU doing the actual work, while the control unit decided when to do it. Now talking about the fetch execute cycle. So every CPU follows the same response and the same repeated cycle thousands or millions of times per second. So first one is the fetch. The program counter points to the next instruction. The CPU loads that instruction into the instruction register. And the second one, so instruction register is also known as IR. And the second thing is decode. The control unit figures out what needs to happen, which arithmetical logical unit operation, which register to use, and where data is located. So third one, it's execute. So the arithmetical logical unit carries out the operation. The fourth one, it's store and repeat. The result goes back into memory or a register, and the program counter moves to the next instruction. So this thing typically happens for every single machine instruction your program generates, and it runs. Um, the and then there comes the memory, the unified storage model. So von Neumann's major breakthrough was storing both programs and data in the same memory. Today, though this feels like pretty obvious, but at the same time it completely changed how computers used to work. So in this memory, program instruction lives here. So variable and data structures also lives here. Stack frames for function calls live here. Heap allocated objects also live here. So this means the CPU does not treat code and data differently. Both are just sequences of bits at memory address. And about the memory hierarchy. So modern computer enhanced this memory system with a hierarchy to reduce the bottleneck. So from the fastest to the slowest we have the registers, which are typically the fastest and the smallest bytes. And the second one is the cache, the L1, L2 and L3 caches. So they are very fast from kilobyte to megabyte. And the third one is main memory. So that is also known as RAM or random access memory. So this is also the fast access or it's in gigabyte. And the fourth one is secondary storage. So it's the slower but persistent terabytes. So this idea is simple. Keep the most frequently used data closer to the CPU so it doesn't need to wait. So this hierarchy is a direct response to the limitations of the original architecture. And the slide 9 is the von Neumann bottleneck. So the biggest issue with the architecture is that the instructions and data must share one single bus. So this means the CPU often waits for memory to catch up. CPUs today can execute billions of instructions per second, but memory can only supply data a fraction of that speed. So as programmers, we actually feel this bottleneck when our program slows down due to cache misses or inefficient data access patterns. So what are the solutions for this bottleneck? So to overcome this bottleneck, modern CPUs use several different techniques. So first one is the cache memory. So cache memory stores recently used instructions and data extremely close to CPU. And the second one's pipelining. Pipelining allows multiple instructions to be processed in different stages at the same time. And the third one is parallel processing. So parallel processing uses multiple cores working together. And the fourth one is branch prediction and speculative execution. It guesses future instructions to reduce delays. So these innovations allow modern computers to remain extremely fast, even with the bottlenecks still present. So now we got von Neumann versus Howard architecture. So von Neumann machine, they use only one memory for code and data, whereas Howard architecture uses two separate memories, allowing simultaneous access. So this makes Howard system very efficient for embedded device like DSPs and microcontrollers. So on the other side, modern CPUs combine both. So they look like von Neumann machines to us in terms of physical appearance, but internally they use Howard style separation instruction and data caches. So talking about the programming implication, this architecture affects how we write efficient programs. So first one is the cache-friendly code. So cache-friendly code performs much faster. Sequential memory access is better than the random access. Deep branching can hurt pipeline performance. Buffer overflows are possible because instruction and data live in the same memory. So understanding this architecture helps us write safer and faster code. So now let's give a real world example. So a simple Java loop, like summing in turns, goes through all the steps we've discussed: compilation, loading into memory, setting the program counter, running the fetch execute cycle for each machine instruction, and finally storing results. Even shorter programs involve dozens or hundreds of machine level instructions following the von Neumann model. So, talking about the modern evolutions and future directions, today, new architectures like quantum computing, neuromorphic chips, and processing in memory are being explored. So, quantum computing, fundamentally different architecture using qubits instead of bits, no traditional fetch execute cycle, potential to solve problems intractable for von Neumann machines. And the second one, also the neuromorphic computing, hardware that mimics brain structure and functions, computation and memory integrated like biological neurons. So it has massive energy efficiency and promises massive parallelism. So, however, the vast majority of computers still rely on the original von Neumann approach. Its simplicity, flexibility, and compatibility with modern software makes it incredibly enduring. So, to talk about the key takeaways, or to wrap up, von Neumann introduced the unified memory model that changed the computing forever. Programs and data share the same storage space, so every instruction follows the fetch execute cycle. And the third one is the shared bus leads to the famous bottleneck. The single bus between CPU and memory creates performance limitation that modern systems work hard to overcome. And fourth one, it is still relevant today. 80 years later, this architecture remains the foundation of virtually all computers that we program. Modern solutions make CPU extremely fast despite these limitations. So even after almost 80 years, the von Neumann model remains the foundation of computer architecture today. So that's my time. Thank you, everyone.